Welcome, everyone. I'm Tyler Lund with Veris Technologies. Today, we're going to go through three simple ways or simple explanations, maybe, of how sensors, soil sensors, can improve carbon farming and reduce greenhouse gas emissions. So, it's not a big surprise that the first way that sensors can help is that they can accurately measure soil carbon stocks. The right sensors can accurately measure the amount of carbon in a field for baseline and then to see how much it's changed. We're not going to go into the details of how the sensor technology works that Veris uses, but we're going to go into more just if we use sensors, what's the impact. Another way it's helpful to have a soil map from sensors is that the cost of going to collect that data is not just borne or shouldered by the carbon. We can use this data for a lot of different applications on a farm. The third way is that nitrogen use efficiency can be improved when we guide our nitrogen management strategy using high resolution soil sensor data. If we can keep that nitrogen in the ground instead of in the atmosphere, that's a great thing for everybody involved. If you've been around precision ag, gone to conferences, seminars, you've probably seen this quote: "You can't manage what you don't measure." And we're changing this, in the carbon space to you can't monetize what you don't measure. Farmers aren't going to be paid for or rewarded or be able to comply with regulations if we can't measure that carbon. And the people who are saying that is the carbon buyers, right? They want to make sure that if they're paying money, it's for carbon that's in the ground. Policymakers, if we're going to have a positive role as farmers in the carbon space, it's going to be because we actually can measure it. And farmers are actually saying this too. They're not going to participate in programs that aren't scientifically backed. They don't actually do a good job of measuring the amount of carbon they sequester. You can see here, right, when a farmer brings their product, the crop, to the elevator, they weigh when they're full, they weigh when they're empty, and they get paid for what they bring to the elevator. Same should be true for carbon farming. They should be able to be compensated for what they bring, and we do that better when we have lots of measurements from sensors. All right, so we got to first establish the problem, right? What problem is there? Well, in farm fields, you take this field, break it into 2.5 acre, 1 hectare grids, and take 10 samples. This is something you can do yourself. And what you will find is there's a lot of variability of carbon and organic matter. Here it ranges from 1.8 to 4.4, and there's this one. And this is something you find across the field, you find across the globe. Carbon is highly variable, especially when you take into consideration that the amount of carbon that we're going to sequester over 5-10 years is not that great in terms of when you compare it to the spatial variability. So if we're going to move carbon from 2 to 2.5 or maybe even 3, there's still in 1 hectare there can be 3 to 4% organic matter carbon differences. So what we see is the variability in distance is actually greater than the variability, the amount we're going to change in time. So we have to do a very good job of characterizing these fields, getting the carbon measured. The concept's pretty simple, right? If year 1, we take a measurement, we got soil carbon, 10 years later, 5 years later, we measure again. Hopefully, right, the soil gets darker, we got more carbon there. However, this is not what we get paid for as farmers, right? This is not the end game. We have to take into consideration the margin of error or the confidence interval based on how many sensor readings we took. We can see it swallows up a lot of that difference depending on how you measure. So if we want to be able to monetize this carbon, we have to measure it in a way that shrinks the margin of error or improves the confidence interval. That's when we have opportunity as farmers. The way we do that is with more readings. Right? It's a simple equation to get at the confidence interval. When we increase sample size, we do a much better job. And we cannot do that with sampling alone. Labs are important. They validate, calibrate sensors. However, the volume is going to be collected with sensor readings because it can be done cost effectively. It can be deployed rapidly. And what it does for the farmer, it minimizes the discount of uncertainty, right? The uncertainty that a buyer or a policymaker has is right in here. And when we can minimize that, we can maximize the return for the farmer. So that's the first way. And I want you to actually see it in the field too. You can see the difference between the measurement techniques, right? Soil sampling is a laborious process. I don't know if this is in slow motion or just the end of the day, but it takes a lot of work to collect lab data. Sensor data, on the other hand, with an automated system like the Veris core scan, stop without the operator even having to get off the vehicle. It goes down, takes a reading every centimeter. So we're getting more data faster, a lot easier. That's what it looks like in the field. If you the data wise, right, one day's worth of work, we're going to be able to collect that much data. So that's going to impact what our confidence interval. Look at this, all the sensor data, and this is just a fraction of what's actually collected on a field. Just massive amounts of sensor readings to be able to improve that prediction. And because we're taking so many readings, we're actually able to shrink this sampling down because of that automated nature of that core scan. We can get 1 acre grids at 50 acres an hour, and we can make a 3D characterization. And if you look at all the sensors, it's not just one soil property. We're measuring the most important physical, biological, chemical properties, topography. All of this really means we've completely captured that field, and not just for carbon, right? That's the second point, is that there are multiple practical ways that this can be used to help farmers. Agronomists, consultants, farmers can implement this to improve their operation. The most kind of well-known one, right, is the input agronomy. That's putting the right order: seed, fertilizer, irrigation, drainage. All the inputs can be optimized based on soil. One new emerging one is implement agronomy. This is making sure that planter is set perfectly, and the tillage tool set to account for the soil conditions. Regenerative agronomy, that's what we're talking about, right? The making baseline measurements, benchmarking practices. We're able to do that with good measurements. So when we have that data, we can do a better job of putting the right amount of herbicides, irrigation, water management, soil amendments, choosing the right hybrid, and then nutrients. And the nutrient we want to focus on here is nitrogen use efficiency. 50% of the nitrogen we're applying is going into the crop, 50% is being lost, some of that as a greenhouse gas. One of the best ways, or the simplest way, most common way people are using soil maps to improve nitrogen management is that on their field, they've got areas of the field that have real high potential and medium and low, and they're putting the amount of nitrogen that is justified based on that potential. So certain soil characteristics contribute to high yields. Let's challenge those areas and let's pull back in the more marginal areas. So just a simple yield goal based on soil map. Here's just a nitrogen credit map. Organic matter, 1% of organic matter in the growing year mineralizes, produces free nitrogen, 20 to 30 pounds of free nitrogen for each 1%. And so we can take that into consideration when we're choosing our rates to apply, because we know we're going to get some credit from that organic matter mineralization. Another one is just thinking about what areas of our field are most prone to nitrogen loss through leaching and denitrification. And we're mapping out those characteristics, right, where there's sandy soil on a slope and we can lose nitrogen through the profile. Or on the other side, heavy soils that might stay saturated and can denitrify, turn that nitrogen into a gas. These maps can be used to interpret imagery, whether that's from a drone or satellite. They can be used for sampling, targeted sampling. And all this data, all these soil maps can be incorporated into a nitrogen model that it includes weather, yield goal, farm practice, all of it encompassing. But if we have good soil as a foundational layer, it improves the output from those models. The last thing I want to share is just thinking about holistically that these soil maps, again, are just not based on just compliance with MRV protocols. They enable a lot of different things to be improved on a farm, on the farm and off the farm benefits from good soil maps. We didn't go into any detail about how the sensors work, how accurate they are. If you are interested in that, please reach out to us. Check out some of our other videos. We're happy to share some scientific papers and walk you through how these sensors really can measure carbon and help improve a lot of inputs. Thanks so much.